Hi, and welcome to the Low Level Devil channel. Today we're back on the Raspberry Pi Bare Metal series. Many of you have requested a demo of how to use the I2C or I2C protocol, so that's what I'm going to do today. If you aren't familiar with I2C, it's a serial communications protocol for communicating with devices. Many devices support this protocol from a wide range of uses, everything from memory and storage to sensors and displays. So if you want to use any of those kinds of external devices, understanding a serial communications protocol like SPI or I2C is important. So if you want to know more about the low-level details on how I2C protocol works, I'll put a link in the description to a good video overview. We won't really need to know those details to use the Raspberry Pi because it has a hardware implementation of the protocol. We just need to interface with that hardware using its memory map registers. Now, since I2C is a protocol used for communicating with external devices, we're going to need an external device to connect to. Since we're just getting into understanding how to use it, I'm going to try to keep it simple, and we'll use a simple Arduino script, and that'll create a slave device, an I2C slave. Our Raspberry Pi will be the master. So I'm going to be using an Arduino Nano to run this on. The script should work on an Arduino Uno or a Nano. I'll put a link to where you can buy one cheaply in the description if you don't have one already. The connection between the Raspberry Pi and the Arduino is very simple. Simply connect the GPIO2 on the Pi to the A4 pin on the Nano, then connect GPIO3 to A5, and then connect a ground pin from the Pi to the Nano. So now let's get started on the code. So first we're going to open up the BCM2835 datasheet into the BSC section, which is the Broadcom serial controller. And this has an implementation of the I2C bus interface. And there's more details about it in here if you want to know more about it. But essentially it's a memory mapped device. So as you can see here, it says it has 8 memory map registers, and there's 3 different buses, BSC 0, 1, and 2, and we're going to be using 1, which we need this address 804000 appended to the end of our base address. So you can see here we have a control, status, data length, slave address, FIFO, clock divider, data delay, and clock stretch timeout. So those are the 8 memory mapped registers we're going to need to operate with. And if you scroll down here, you'll see more details about each individual register, what all the different bits setting and reading will do on each of the registers. Like you have the error here, RXF. So these are all the different bits on the registers that we will be interfacing with, and data length register is pretty straightforward and obvious. So let's go back here. Oh, I scrolled up too far. Yeah, so let's actually map this into code. So first we're going to create, in our peripheral section, we're going to create an I2C.h file. Start, of course, with our pragma once. Include the base. And we'll include common header. So now let's start with a struct for those registers. And the very first register was control. Then we had status, data length. We have slave address, the FIFO, the divider. Then we have a delay value. We're actually not going to use all these. Let me see, what's that last one? Clock stretch timeout. So we'll just call it, let's see, call it clock stretch. We only need to use a few of these actually. So, and now we're going to actually create a define, just like we did for GPIO and the timer and IRQ. So this is just a reference to our registers from the base memory address, pbase plus 0x0084,000, which is what we got from that data sheet. Now we're also going to take some defines here. I'm just going to paste into here, and these defines are just going to be the different bits to set. So bit 15 for the I2C enable. If we look at the individual registers, we'll see here bit 15 is the I2C enable, then int R, int TT. You'll see we have one for each of those. These are just defines to make it easier for us to know what we're doing instead of just putting random bit shifting around in our code. So now let's create an I2C header in the main include section. This will be our actual interface that the kernel will use. So again, we include the common H. So we'll start with an enumeration. This is going to be the status. These are different status values that I2C can return when we send or receive a command. So the first one, we're going to just call it success. Then we'll see an ACK error, which is an acknowledge error. And then let's say data loss, if data was missed. Then we're going to have a clock timeout. I think that'll do it for those. So now defining the interface, the first thing we're going to do is init. So that'll initialize it. Then we're going to have an I2C receive, which will take in a slave address, a pointer to a byte buffer, and then the size, and it returns that I2C status value. And we're going to have pretty much exactly the same thing with the send. It'll take an address, a buffer, and a size. Okay, so that's our simple interface for it. Now what we want to do is create an implementation, so we'll create an I2C.c. This will be the implementation of that protocol. So I'm going to copy and paste our interface into there. First, of course, we want to include it. We're going to include GPIO.h because we'll need to use the GPIO when we're include our peripherals I2C, our main I2C header, and let's also put a printf in case we want some debug statements. Now I'm going to define the actual speed of I2C that we're going to use, and we're going to use the 100 megahertz version, so it's 100,000. Paste these values in here, and we can get started on the implementation. Now to start on this implementation, I'm going to go to the alternative function assignments section of the datasheet. You can see here we have SDA0 and SCL0. That's for the very first BSC, but we're using BSC1. So we want these GPIO 2 and 3, and they're using Alt0 for both of those. So those are the two different alternative functions that we want to set on the GPIO pins. So for 2, we just want to set that to GF Alt0, and the same thing for 3. Then we want to enable those 2 pins, so enable 2 and enable 3. And another optional thing we can do is set the speed. By default, it actually uses 100,000. So we're going to set our divisor to the core clock speed divided by our I2C speed. And again, this is optional just because by default it uses 100 megahertz. Also, that clock core speed isn't configured, so I'm going to put it down here in the base.h, and that core clock speed is 1.5 gigahertz. So I'll just enter that number in here. That'll be our define. Alright, so let's go back to the I2C.c file. And yeah. Alright, so we're good with the init function. That's all that's needed to initialize I2C. So now we want to start on the receive to receive a message from a slave. So we'll start with a count because we put in the size. We want to count the number of bytes that we're receiving. So first we want to set the slave address to the address we passed in. The next register we need to set is the control register. We need to clear the FIFO buffer. So setting this flag on it will clear that FIFO buffer. Next we want to set the status register to CLKT ORed with SR ORed with SDone. And now we can set the data length to the size that was passed in. And now that the FIFO is cleared, we can set the control again. This time we're going to set it to I2C enable ORed with ST ORed with read. So that's going to get it ready to start reading data. So now in order to read data, what we're going to do is loop while reading the status register while it's not done. We are going to then loop while reading the status register again to see if the RXD flag is set, which is the read transfer flag. And if it is set, we want to dereference our buffer ++ equals the value in FIFO, but we only want the first byte, so we're going to mask it with FF and then increment our count. So now another thing that we're going to need to do is after that we want to loop while count is less than size and the status SRXD flag is still set, because it might have set the done flag already, but there's still data to be processed. So we just again want to take that same code from there and read the bytes off of the FIFO. Now we want to grab the value of the status register to see if everything was successful. And then we want to set the status register to done. So status equals SDone. Now based on that status value that was returned, we're going to return different codes from that enumeration we had. So if the SERROR flag is set, we'll return, let's see, it was ACK error. And we'll do else if the, let's see, there was a timeout once. If CLKT is set, then we know there was a clock timeout. Else if, and no, we need to check if the count is less than size, then we didn't get all the bytes that we needed to get. So then we're going to return that data loss. And then finally we'll just return success if none of those passed. So that's it for the implementation of receive. And now send is going to be very similar. So we'll start with that. And actually we want to set a lot of these same register values, and we do need a count as well. So I'm going to paste these in here. A couple minor difference. Let's see, these are all the same. We just need this read flag gone because we're not going to be reading. This would indicate that we're going to be writing. So now we're going to actually do something very similar that we did in read. While it's not done, we want to check the TXD flag. See if we can transfer data. And if we can transfer data, we want to essentially do the opposite of what we did when we read from it. We also want to only do this while count is less than size, because we don't want to keep reading after the number of bytes that we want to read from that buffer. So let's see, for this we'll do regs I2C. The FIFO is equal to dereference our buffer plus plus, which is essentially the opposite of this. And I think that should be it, other than checking our success values, which we're going to do the exact same thing. Read the success, set it to done, and check the values for it. And I think it looks all in order here. So let's see if we can actually compile it. So open up a new terminal and call make. Okay, looks like we got an error here. Typedef enum. And looking at the enum, everything is right. So looking at the peripherals header, it looks like we're just missing a semicolon there. Very common mistake. Now if we make... Okay, now that that compiles, I want to give you a quick look at the Arduino sketch. I'm going to kind of breeze over it because this really isn't about Arduino, but so at the top we have a wire.h we're including. We have address 21 we're using for our slave address, a little message here. So in our setup we call wire.begin with the address. We have an on request and on receive and functions that we point to for those. The serial begin using 9600 baud and a message. So now our receive data, while there's data available on the wire, we're going to read it, and we're using a buffer with sprintf to just show what the value of this red byte is. We have a hex value and a character value. So that's all it's going to do, is just print whatever sent to it. Now the request data, essentially we're going to take this answer here, which is just a simple string. We're going to send the answer and the strlen of it, and we're just going to print out that we sent it, and we're going to put a little delay in our loop. So now we want to upload that to our Arduino, and you can actually bring up the serial monitor here. Just make sure your baud rate is set to 9600, and you'll see the little message there. So now that that's ready, let's code to this serial interface. So we'll start with the kernel. We can get rid of a lot of this stuff from the previous lesson, all these different sleep operations. So the first thing that we're going to want to do, well, let's actually just print out that we're initializing the I2C protocol. See, initializing I2C. Okay, and we're just going to simply call I2C init. We're actually going to need to include the header though. So include I2C.h. So now that we've initialized it, let's send some data, or actually just read some data. So we're going to loop 10 times and call the read function. And if you remember from the Arduino sketch, whenever we read, we're essentially going to get the data I2C hello back, or hello I2C, whatever it was. So we have 21 for the slave address, which is what we had in our sketch, and then the buffer. So let's see, address 21, hello I2C, which is 9 characters. Yep, 9 characters. So in our char buffer, we're going to read those 9 bytes and set the buffer 9 to 0 so we can print it out. And we'll just print out saying that we received %s and the value that we received from the sketch. And then we'll just do a timer sleep for 250 milliseconds. So now that we've received data, let's send some data too. We'll use a U8, D equals 0, D is less than 20, D++. And we'll do I2C send, again address 21, and the address of D, and then 1, because we're just sending 1. And again, we'll sleep for 250 milliseconds. And we'll print out saying that we sent and the value that we sent. Alright, now let's send a longer message. We'll send hello slave device. So this will come from the master, and the slave device should print it out. Alright, so, and that's 18 characters, so that's the length we're putting in. Now let's go ahead and run make. And it looks like there was an error. Oh, I put int before U8. There we go. So now it should build. Make clean, and then we'll make, and it's all ready to go. So now let's test this out. Okay, so now I put my disk in the Pi 3, and I'm opening up the screen command. We can see it booting up. Let's see, here we have received hello I2C 10 times, sent 0, 1, 2, 3, 4, 5, all the way up to 19, and then done. Now if we look at the I2C sketch, we can see all the logs from there. Actually, let's clear this, and we'll run them together so you can see it a little better. So I'm just restarting the Pi again. Now you see sent data, well, it's receiving data, and then it received that hello slave device. And there you have it. So now let's, I'm going to put some notes here in the code as well for what the different connections are between the two. Let's see, we had our Pi and connecting to the Arduino. So we have GPIO2 connects to A4, GPIO3 connects to A5, and just connect a ground to a ground. And there you have it, a simple I2C connection between the Raspberry Pi and an external device, and how to control it using memory mapped registers. That'll be enough to get us started with I2C. Possibly in a future video I want to go over connecting to an actual device, maybe a sensor or an LCD display. But for now I think that's a good intro to the I2C communication protocol for our little bare metal project. So again, if you learned anything and enjoyed this video, like and subscribe. And if you have any questions or anything, comment on the video or join our subreddit. And thanks again for watching.